Hello everyone, my name is Nur Shazwani bin Tasmi, metric number 171-42028. Today, my group 6 will present on our topic given, which is laser cooling and laser trapping. First of all, I would like to introduce my group member. My name is Nur Shazwani bin Tasmi, and next.
Hi, my name is Alif Izzuddin bin Ayub. My metric number is 171-46452.
Assalamualaikum and hi, I'm Amira Basir with metric number 17145870.
Hi, I'm Saibah Nabihah binti Muhammad Baharudin, metric number 17146639.
Hi, my name is Ahmad Shili Zamani bin Ahmad Nazri and my metric number is 17161255.
First, we start with the part 1, which is the basic concept. In 1975, Theodore and Arthur were the first physicists that proposed to cool neutral atoms in pairs of counter-propagating laser beams detuned slightly below a resonance transition of the atoms and able to explain that using the concept of Doppler effect. The first test, William Phillips was the first to develop the Zeeman slowing technique. By using chirp cooling method, Stephen Chu was able to slow down the atoms and he used optical molasses trap to confine atoms for the first time, while Clark was the one who developed his first cooling method. Therefore, in 1997, these three figures were awarded with Nobel Prize in Physics for the development of methods to cool and trap the atoms. When we mention about laser beams, normally we think of it as heating something instead of cooling it. However, in this presentation, we will show you how laser beams can be used to first slow down atoms and then trap them. First, I will explain about the basic concept to help you understand the technique behind it. So what is photons? Light is an oscillating electromagnetic wave and consists of particles that are called photons. Laser light has a special property called coherence. Particularly in laser beams, the individual photons all have the same frequency, in phase with each other, and are traveling in the same direction. To cool the atom means to slow it down, but how do we do it? Here the concept of Doppler shift is used. In the context of light, an observer will perceive a Doppler shift in the frequency of light if the source of light is moving relative to the observer. Doppler shift in laser cooling is a way used to control whether or not an atom will absorb a photon, depending on whether the atom is moving opposite to or in the direction of the laser beam. Relating this to that of laser cooling, the basic principle is that absorption and subsequent spontaneous emission of photons lead to light forces. These forces become velocity dependent through the Doppler effect.
The principle of how a magneto-optical trap works lies in a mechanism called Doppler cooling. By tuning the laser light to a frequency just below the atomic resonance frequency at which the atom absorbs photon from the laser beam. In each absorption event, the atom loses a momentum equal to the momentum of the photon. The atom, which is now in excited state, will emit a photon spontaneously but randomly in direction. Momentum is now returned to the atom. The net result of the absorption and emission will always reduce the speed of the atom, on the condition that its initial speed is larger than the required velocity from scattering in a single photon. If the absorption and emission are repeated many times, the mean velocity and therefore the kinetic energy of the atom will be reduced. Since the temperature of an atom is a measure of a random internal kinetic energy, this is equivalent to the cooling of the atoms. If the atom initially at rest, and for simplification, let two energy level of the atom be called as E1 and E2, and the laser beam coming at negative and positive x direction with a frequency of omega L. Photons with energy equal to the difference in energy between E1 and E2 are most likely to transfer their momentum to the atom by way of absorption and spontaneous emission. By tuning the frequency of the laser beam omega L to produce photons of energy that are slightly lower than the energy difference between E1 and E2, this can ensure that the atom at rest between the laser beam will on average absorb equally amount of photon from both lasers. This causes the atom to experience equal forces from each direction. Hence, an atom at rest experiences the same frequency omega L from both laser 1 and laser 2 and does not feel a net force from the laser beam. For moving atom between the intersecting laser beam will experience different frequency from laser 1 and laser 2 due to Doppler shift. For an atom moving to the left inside the trap series and increasing in the frequency of laser 1, omega 1, because it's moving against the direction of the propagation of light from laser 1. And at the same time, the atom experiences a decrease in the frequency of light from laser 2, omega 2, because it is moving in the direction of light propagating from laser 2. This ensures that the atom absorbs many more photons from laser 1 than it does from laser 2. Absorbing more photons from laser 1 effectively reduces its leftward velocity, and absorbing few photons from laser 2 ensure that the atom cannot be accelerated to the left. By the same reasoning, an atom moving to the right experiences an increase in the frequency of laser 2, omega 2, because it is moving against the direction of the propagation of light from laser 2. At the same time, it experiences a decrease in the frequency of light from laser 1, omega 1, because it is moving with the direction of light propagation from laser 1. The atom does not absorb nearly as many photons from laser 1 as it does from laser 2, which reduces the atom velocity and ensure that it cannot be accelerated to the right. For cooling experiment setup, it consists of injection locking system, dichronic atomic vapor laser lock, saturation spectroscopy, and trap cell. First, the trapping laser will be split into two beams with equal intensity by polarizing beam splitter and reflected by mirror to send out of injection locking system. The collimated beam is then traveling to a system of auxiliary optics where the beam undergoes several polarizations and reflections. When the beam enters the trap cell, it will first be divided into two beams, one in Z direction and another one in XY direction. Beam in XY direction will be further split into X direction and Y direction by polarizing beam splitter. Before this beam enter vacuum chamber containing, for example, rubidium atom, they will pass through quarter wave plate, which convert linearly polarized light into circularly polarized light. The circularly polarized laser beam will be reflected by mirror in a way that causes them to intersect perpendicularly inside the vacuum chamber from each direction in space, allowing them to cool the rubidium atom inside the vacuum chamber.
Hello everyone. So I'm going to explain on the third part of the presentation, which is the Doppler limit. The frequency of the 6 laser beam in the optical molasses can be reduced so that only the slowest atoms are confined. However, since the emission of a photon from an excited atom is from random direction, the atom can gain momentum from this emission. When there is equilibrium between laser cooling and the heating process arising from the random nature of both absorption and emission of photons, the Doppler limit arises. Now that we are clear how Doppler limit arises, which is a result from equilibrium between laser cooling and the heating process arising from the random nature of both absorption and emission of photons, now we are going to find what is Doppler limit. Doppler limit is defined as the minimum temperature achievable with Doppler cooling. However, this limit is only applicable for a simple two-level structure atom. Meanwhile, the temperatures below the Doppler limit can only be achieved by using another method called as Sisyphus cooling method. But you must note that this method can only be applicable for a real alkali atom with lack of hyperfine structure, which means that they have degenerate energy level. Next, we are going to find the formula to get the temperature of Doppler limit. First of all, we need to equate the process between cooling and heating. Finally, we will arrive at the first equation. And after a lot of process of substituting and equating, we finally get the equation for the temperature of Doppler limit, which is given by gamma h bar over 2 kb, where gamma is equals to 2 pi 6 megahertz, kb is equals to Boltzmann constant, and h bar is equals to Planck constant.
Atom is remain inside the trap when a palm laser beam incident on the atoms shines slightly higher in frequency than the trap laser beam. Atom absorb photons from the palm laser beam and driven to energy level just below E2, where it can spontaneously emit a photon and fall back to E1. Atoms will drift out of the trap when the rate of atoms falling to a different energy state than E1 is higher than the rate they pump back to E1. Each pair of opposing laser beam contains one left circularly polarized beam, sigma negative, and one right circularly polarized beam, sigma positive. The three pairs of oppositely polarized beam incident upon the atoms from each direction in space make it possible for an applied magnetic field to trap the cooled atoms in one location. Laser cooling method lower the velocities of atoms. However, magnetic field is needed to force the atoms to stay at one point, thus trapping them. Trapping atoms need the application of external magnetic quadrupole field oriented in the condition point of minimum field strength Bz equals to 0 lies at the intersection of laser beam Z equals to 0 as shown in the picture. Same things applied for the x and y axes. First, we let sigma positive as light propagation from laser 1 and sigma negative as light propagation from laser 2. When atom drifts away from the position Z equals to 0, the magnitude of magnetic field increases and the atom experiences increased Zeeman splitting of its energy levels. For simplified example, let's consider an atom with two energy states where first energy state is 0 and has substate level 0 and one more energy state of 1 with substate level of 0 and plus minus 1. The magnetic field causes the splitting of energies for Mj equals to 1 and Mj equals to negative 1 atomic substates, which will be shown in the figure afterwards. If atom is located to the left of Z equals to 0, its Mj1 substate gives the atom a better chance of absorbing more sigma positive photons than sigma negative photons. Absorbing more sigma positive photons causes the atoms to be pushed back towards Z equals to 0 as the sigma positive photons propagate to the right. Oppositely, if the atom located to the right of Z equals to 0, its Mj negative 1 substate will absorb more photons from the sigma negative beam. High sigma negative photons absorbed causes atom to be pushed back toward the Z equals to 0. This picture shows the formation of quadrupole magnetic field. As we know, current in a wire will produce magnetic field. In the case for quadrupole magnetic field, two spools of wire in an anti-Helmholtz coil configuration with current flows through them is used. When current in one loop runs in the direction opposite to the other one, a 0-point minimum arises in the magnetic field between the spools. This field permeates the vacuum chamber that houses the atoms, thus increases the interaction of atoms with the photons.
For the last part, here's an example of technological application for laser cooling and trapping, such as optical tweezers, atomic clock, quantum simulations, atomic interferometer, quantum computer, and Bose-Einstein condensation. But we are going to further discuss on the applications of laser cooling using optical molasses technique, which is atomic clock. The development of atomic clock has led to numerous scientific and technological advances such as regional and global navigation satellite systems and applications in the internet, which depends critically on the frequency and time standards. Also, atomic clock used at some long wave and medium wave broadcasting stations to deliver a highly precise carrier frequency. And many other scientific disciplines has been imposing atomic clocks, such as for long baseline interferometry in radio astronomy. And interestingly, in 1997, Stephen Chu and his friends has made an atomic fountain where cool atoms are launched upwards into a chamber in which they are slowed by gravity. This technique is able to build atomic clock with 100-fold greater precision than currently possible. So what is actually meant by atomic clock? It is basically a type of clock that uses certain resonant frequency of atoms such as cesium or rubidium to keep time with extreme accuracy. The electronic components of atomic clock are regulated by frequency of microwave and electromagnetic radiation. The quantum transitions of cesium atom will be induced only when the radiation is maintained at highly specific frequency. Therefore, these quantum transitions are observed and maintained in a feedback loop that trims the frequency of the electromagnetic radiation, then eventually these waves are counted. The best cesium fountain atomic clock are now predicted to be off by less than 1 second in more than 50 million years. The principle underlying the cesium clock is that all atoms of cesium-133 are identical and produce radiations of exactly the same frequency, thus make the atom perfect timepieces. The timing process begins by introducing cesium gas into a vacuum chamber and directing 6 infrared lasers to compact and cool to a near absolute zero temperature. Then, two vertical lasers are used to notch the atoms up to a meter, which creates a fountain cavity. And lastly, due to the round trip through microwave cavity takes about a second, it has resulted in greater timekeeping accuracy.